All right, welcome back. Today we have a banger of a video planned out. Now, why is it going to be a banger? That's because we're talking about mathematical induction, aka proof by induction. Now, you might be wondering, Johnny, why are you getting so excited about induction, right? Already, we haven't even written anything besides induction. Induction is such a powerful proof technique. I'll be honest with you, right? We've done proof by smallest counterexample. I have not done a proof by smallest counterexample since my discrete math class. Now, I'm just an undergrad, so maybe it'll come up again, but it hasn't yet, right? Proof by contrapositive. Okay, that one has come up a little bit more often, right? But it's never my go-to proof technique. I never get a statement to prove, and I'm like, oh, let me try the contrapositive first. However, proof by induction comes up time and time again in graph theory, combinatorics, in real analysis, in topology, and I'm sure it's going to continue to show up in my classes. It is just that powerful of a proof technique, right? It's powerful because what we do with proof by induction is we show that some property is true for all natural numbers, right? Or maybe not all natural numbers, maybe all numbers greater than or equal to some positive integer, right? And when I say that, like all these natural numbers have some property, right? This is what I mean. Here, this is going to be something that we'll prove. Here, let me write this in blue. If I have something like 1 plus 3 plus 5 plus dot 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 plus 2k minus 1, so we've got odd integers, is equal to k squared, I could show that this is true for all positive integers by using a proof by induction, and we're going to. So what are the steps for a proof by induction? Here's what we're going to do, right? First things first. What we're going to do is we're going to let A be the set of natural numbers for which the result is true. The result being stuff like what I have written in blue. Now, currently, A is empty, right? We haven't shown that the result is true for anything. So naturally, the next step is to show that A is non-empty. So what I'm going to say is show 0 is in A. And the reason I'm specifically saying 0 is because when we learn induction, again, we're talking about showing that some property holds for all natural numbers. In our case, that includes 0, so you usually start with 0 and then just go up from there. But as I mentioned, in some cases, you don't always start with 0. Sometimes you just show for positive integers, like what we're going to do, and we'll start with 1, right? And this is going to be our base case. So always what we start with, base case. All right, what is the next step? Our next step, right, is to show, right? Show if k, which is going to be some positive integer, some natural number, show if k is in A, then k plus 1 is also in A. Now, this step right here is called the inductive step, right? And how do we perform our inductive step, right? There's two little things we got to do, right? What we do is we use our assumption that n equals k is true. So assume the result is true. The result is true for n equals k, right? This is called the inductive hypothesis, right? The inductive hypothesis. And the reason I'm giving all of these names is because we're going to refer to these in our proofs. We're going to say, oh, by the inductive hypothesis, or like by the base case, right? So it's important that we have these names. So we assume that the result is true for n equals k, or k is some natural number. That's the inductive hypothesis. And the next thing we do, right, is we use this. So we use this hypothesis to show that we use this hypothesis to show the result is true. Result is true for n equals k plus 1. Now, what does that mean? It's not really important. We're going to show that with the example. It's way easier to learn through exercises and examples. So we assume it's true for n equals k. We use the hypothesis to show that the result is true for n equals k plus 1. This kind of looks like a u. For n is equal to k plus 1. And now finally, we conclude that skipped ahead, that A is the set of all natural numbers, wait for it, all natural numbers greater than or equal to our base case. The reason I specify that, again, is because our base case might not always be 0. It might be 1, it might be 2. Your professor might try to trick you and throw in multiple base cases that you have to cover. I'm not going to do that, but watch out for that. You might have 2 or 3 base cases you have to look for. So this is our proof by induction. And so the first thing I'm going to do is prove that that equality holds, the one written in blue, for all natural numbers greater than or equal to 1, right? And what we're going to do is use this exact template to do that, right? So let's say this, right? Let's rewrite what we have. 1 plus 3 plus 5 plus ... plus 2k minus 1 is equal to k squared. Actually, let's replace these with n's right now. 2n minus 1 is equal to n squared. So basically, I'm saying that the sum of the first n positive odd integers is equal to n squared, right? And now here's what my proof is going to be. And we're going to literally do this step by step, right? We're going to say, okay, let A be the set of natural numbers for which the equality is true, right? That comes directly from what I wrote, right? This is exactly what I said would be the first step of a proof by induction, right? A be the set of natural numbers for which the result is true, right? So what's our next step? Our base case, right? So we're not actually going to show that 0 is in A because look at this, right? Look at 2n minus 1. If n is equal to 0, 2n minus 1 is negative. We can't have negative numbers. We're dealing with positive odd integers, right? So we're going to start with n equaling 1, right? So here's what I'm going to do. I'm going to say base case. This is something you could write out in your proofs. You could write base case, colon, right? Let n equal 1, right? Then 1 is equal to 1 squared. So 1 is an element of A, right? There we go. That's our base case. We show that A was non-empty, and we show that the result is true for a natural number, right? Now, what was the next step? Let's see. Assume that the result is true for n equals k. That's our inductive hypothesis. And then use that hypothesis to show that the result is true for n is equal to k plus 1. So let's write this out. Inductive hypothesis. Inductive hypothesis. Assume that the equality holds for n equals k. Now, I'm going to pause for a second. You might be wondering, Johnny, why is it that we can do that? Why can't we just assume that it holds for n equals k, right? Well, the reason we can do that now is because of the base case, right? Because k, right, could just be 1, right? We showed that the result is true for a natural number, so we can just assume that it holds for n is equal to k, right? Because again, let's just say that k is equal to 1, right? And I'm going to go back to this when we show that n is equal to k plus 1, right? So that's our inductive hypothesis. Now let's take the step, right? Inductive step. Okay. So here's what we're going to say. By the inductive hypothesis, And again, in the hypothesis, we're assuming that the equality holds for n equals k. So by the hypothesis, we could say this is true. 1 plus 3 plus 5 plus ... plus 2k minus 1 is equal to k squared holds, right? Now, what exactly do we want to show, right? We want to show that here's what we want to show. We want to show this. We want to show that 1 plus 3 plus 5 plus ... plus 2k minus 1 plus, and now we want the next odd integer, so the next odd integer would be 2k plus 1 is equal to k plus 1 squared. This is what we want to show, right? So how are we going to do that? We're going to use our inductive hypothesis. We can add, here's what we could do. We can add 2k plus 1 to both sides of the equality, right? Both sides of the equality, balancing the equation to get, let's write on the next line, 1 plus 3 plus 5 plus ... plus 2k minus 1 plus 2k plus 1, write that in parentheses, is equal to k squared plus 2k plus 1, right? And now we could say, well, k squared plus 2k plus 1 is equal to k plus 1 times k plus 1, which is equal to k plus 1 squared. Thus, 1 plus 3 plus 5 plus ... plus 2k minus 1 plus 2k plus 1 is equal to k plus 1 squared as desired. So the result holds. The result holds for n is equal to k plus 1, right? And that is exactly what we wanted to do, right? We use this hypothesis to show that the result is true for n is equal to k plus 1. And now, finally, we conclude that a is the set of all natural numbers greater than or equal to our base case, which is 1, right? And why can we do that? Before I write that out, why is it that we can do that? Well, like I said before, when we assume that the equality holds for n equals k, we can do that because of our base case, right? Because k can be 1, right? Because we showed that 1 is in A. So, and now we just showed that the result holds for k plus 1, right? So, because we know it held for the integer 1, now we know it holds for 2. But now just say that n equals k is equal to 2. Again, we show that this holds for k plus 1, so that means this holds for 3. Now just say that n equals k is equal to 3. We show that it holds for k plus 1, so we know it holds for 4. And so we know it holds for 5, and 6, and 7, and for all natural numbers greater than or equal to our base case. I really hope that that clicked in your head, otherwise I just sounded really dramatic for no reason. If it didn't, pause the video, digest the information first, and then move on. But if you get it, so the result holds for n equals k plus 1, thus A is the set of all natural numbers greater than or equal to 1. Greater than or equal to 1. I guess I could have just said all positive integers. And I'll say, this is the set of all natural numbers greater than or equal to 1. And the result holds. The result holds for every positive integer, right? Because it's going to hold for everything that's in A. And this right here is the end of the proof. There we go. Now, you see why that's so cool? First of all, we get to handle these cool problems where we just show things are equal to each other, like the sum of the first n positive odd integers will be equal to n squared. Like, who would have thunk? But it's true. And you see how, I don't know, I think proof by induction is just such a cool technique. Now, what we're going to do is we're going to do another example. So, I mean, if you already understand it, you don't have to keep watching, but I highly consider you do because another example incoming. We're going to swap to a pink pen, right? Okay, so now here we go. What are we going to prove? We are going to show that 2 to the 0 plus 2 to the first plus 2 squared plus ... plus 2 to the n minus 1 is equal to 2 to the n minus 1. Now, again, this is one of those equalities where it's like, well, why is that the case? You know, why? We're going to show you why. We're going to do a proof by induction, right? So, what are our steps for our proof by induction? Let's do proof. Let A be the set of natural numbers, for which the result holds. Say the result is true. Now, base case. Now, in this base case, again, we can't let n be 0 because look at this exponent. We're going to have a negative exponent. We're dealing with positive integers or 0. We're dealing with natural numbers. We can't have negatives. So, what we're going to do is show that 1 is in the set of A, right? So, here's the thing, right? Clearly, 2 to the 0 is equal to 2 to the first minus 1, which is equal to 1. So 1 is in A. There we go. That's our base case. Now, let's do our inductive hypothesis. Inductive hypothesis. Okay, there we go. Assume the result is true. The result is true for n equal k. Exactly like we did last time. Then we're going to take the inductive step. The first step towards showing that this is true for k plus 1. By the inductive hypothesis, this will be true. Let's see. 2 to the 0 plus 2 to the first plus 2 squared plus ... plus 2 to the k minus 1 is equal to 2 to the k minus 1. Now, again, we want to show that the result holds for k plus 1, right? So what we're going to want to show is 2 to the 0 plus 2 to the first plus 2 squared plus ... plus 2 to the k minus 1 plus 2 to the k plus 1 minus 1, so 2 to the k, is equal to 2 to the k plus 1 minus 1. That's what we're trying to show. Just want to remind you. So by the inductive hypothesis, we have that this is true, right? Adding 2 to the k plus 1 minus 1, and I'm writing plus 1 minus 1 just for emphasis, instead of just 2 to the k, to both sides of the equality. The equality gives us, we could just say yields, gives us, let's write this on another line, 2 to the 0 plus 2 to the first plus 2 squared. It's a lot of rewriting the same stuff, isn't it? Plus 2 to the k minus 1 plus 2 to the k plus 1 minus 1 is equal to 2 to the k minus 1 plus 2 to the, yeah, that's what I wanted to add, 2 to the k, and I'm just going to write 2 to the k now instead of 2 to the k plus 1 minus 1 plus 2 to the k. Now, here's the thing. We have 2 to the k's, right? Well, that's just equal to 2 times 2 to the k, right? And then minus 1. Well, 2 times 2 to the k by the rules of exponents is equal to 2 to the k plus 1 minus 1. Thus, we have shown the result is true The result is true. For n equal to k plus 1, thus A is the set of all positive integers. I guess what I could have said is like k plus 1 is in the set A. That's probably what I should have said first. I'm not going to rewrite that. You could just throw that in there. So you could say, thus k plus 1 is in A. So thus A is the set of all positive integers. And the result is true. Or I'll just say, and the result holds for all positive integers. Done. That's the end of our proof. Now, real quick, don't click off the video. I just want to say something about induction. You'll notice that in both of these proofs, proof by induction is very, very methodical. We let A be the set of natural numbers for which the equality is true. Base case. Inductive hypothesis. The only thing that differs really is the inductive step. That's the quote unquote hard part of a proof by induction, is getting from the result holding for K to showing that it holds for K plus 1. But as you can see, it's like such a methodical procedure and it is just so powerful. You need to get good at this because it is going to keep coming up whether you like it or not. Regardless of that, if you made it to the end of this video, thank you for watching. I really appreciate it and I hope you learned something.